I want you to imagine that you are standing inside a vast cathedral at night. There are no candles, no windows, no people, only darkness. And somewhere above you, so high that you cannot see the ceiling, a single point of light appears. At first, it looks insignificant, as a pinprick, something you could cover with your thumb. But as your eyes adjust, you realize that the light is not a point at all. It is a city, not a city of streets and buildings, but a city of galaxies bound together by gravity, wrapped in invisible matter, immersed in gas heated to temperatures so extreme that it glows in X rays. A galaxy cluster, these are among the largest structures in the known universe. And according to the story we have been telling ourselves about cosmic history, building one takes time, a great deal of time. Matter must gather, dark matter must form gravitational wells, galaxies must fall inward, gas must collide, compress, and heat. The entire structure must pass through a long and violent adolescence before it begins to resemble the enormous, organized clusters we see in the nearby universe. That is the expectation. And then NASA looked farther back. Using the James Webb Space Telescope and the Chandra X-ray Observatory, astronomers identified a remarkably developed galaxy cluster in the early universe, seen when the cosmos was only about 1 billion years old. And this is where the story becomes uncomfortable. NASA described the cluster as surprisingly mature. The observations suggest that massive cosmic structures like this may have started assembling 1 or 2 billion years earlier than astronomers had previously expected. I want to be very careful with those words. This does not mean Einstein has been disproven. It does not mean the Big Bang is wrong. It does not mean scientists opened a telescope image and discovered that physics had failed. What it means is more interesting. We may have found a structure that forces us to reconsider how quickly gravity, dark matter, gas, and galaxies can organize themselves after the beginning of cosmic history. And when an object appears earlier than your model expects, one of two things has happened. Either nature found a faster path, or your map is incomplete. And that is the door. And tonight, I want to show you why one distant cluster could become a test of some of the deepest assumptions in modern cosmology. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to explore the places where observation presses against the edge of theory, you are in the exact right place. Now, I want you to imagine an old wooden table. On that table are thousands of iron filings. Beneath the table is a magnet. You cannot see the magnet. You cannot touch it, but the filings move. They gather into patterns. Empty regions appear. Dense knots form. Long chains connect one concentration to another. If you had never seen a magnet, you might still infer that something invisible was organizing the visible material. Hold on to that image, because on the largest scales, the universe behaves in a strangely similar way. The stars and glowing gas we see are not the majority of the matter. Most matter appears to be dark matter, an invisible component that does not emit or absorb light in the ordinary way, but reveals itself through gravity. In our standard cosmological picture, tiny fluctuations in the density of the early universe become the seeds of later structure. Dark matter begins to gather around slightly denser regions, and those gravitational wells deepen. Ordinary matter falls inward, gas accumulates, the first stars ignite, galaxies form, galaxies merge, groups become larger groups, and eventually, after enough time and enough gravity, enormous clusters emerge. This sequence is built into the framework known as lambda cold dark matter, usually shortened to Lambda-C. Lambda represents dark energy, the mysterious component associated with the accelerated expansion of the universe. CDM means cold dark matter, matter that was moving slowly enough in the early universe to allow structure to grow from small scales upward. And this framework has been astonishingly successful. It explains the broad pattern of the cosmic microwave background, and it describes the large scale distribution of galaxies. It gives us a coherent story for how an almost smooth young universe evolved into the cosmic web we observe today. That success matters. When astronomers discover something surprising, the responsible reaction is not to throw the model away. A good theory earns the right to be challenged carefully, but the universe, as I have learned time and time again, has a deeply humbling sense of humor. The better our instruments become, the more precisely nature can show us where our simplified expectations begin to strain. And NASA's early cluster is exactly that kind of object. To understand why, imagine trying to build a skyscraper. You begin with an empty lot. First, you excavate, and then you pour the foundation, and steel rises, floors are added, electrical systems appear, glass encloses the building, elevators are installed, people move in. Now imagine returning to the site the next morning and finding 30 completed floors already standing. You do not immediately conclude that architecture is impossible. You ask a more practical question: how did construction happen so quickly? That is what astronomers are asking. And a mature galaxy cluster contains several layers of structure that normally take time to develop. There are galaxies, and there is dark matter. There is hot gas between the galaxies. There is an enormous gravitational potential holding the system together. The gas is especially important because it can reveal the depth and maturity of the structure. As galaxies and surrounding material fall into a cluster, gas is compressed and shocked. It becomes extraordinarily hot at temperatures of millions of degrees. That gas emits X rays. Chandra was built to see precisely this kind of universe. Webb, meanwhile, can identify and study extremely distant galaxies whose light has been stretched into infrared wavelengths by cosmic expansion. Put the two observatories together, and you get something powerful. Webb can reveal the ancient galaxies. Chandra can reveal the hot environment in which those galaxies live. One telescope shows you the buildings, the other shows you the city's power grid. And when both tell you that the city is already functioning earlier than expected, the problem becomes difficult to dismiss. Here is the hard truth: the early universe was not supposed to be empty. No serious cosmologist expected galaxies to wait politely for billions of years before forming. We already knew that structure began early. Webb has repeatedly shown us galaxies at astonishing distances, but there is a difference between finding early galaxies and finding a large gravitational ecosystem that already appears substantially assembled. A single galaxy can grow rapidly under favorable conditions. A cluster requires cooperation on an enormous scale. Matter across a vast region has to know, gravitationally speaking, where to go. The dark matter halo has to become massive. Galaxies must populate it. Gas must collect and heat, and that process connects the observation directly to one of the central questions in cosmology: how fast can structure grow? I want you to imagine a loaf of bread rising in an oven, and the dough begins almost smooth. Tiny bubbles form, some expand faster than others. Eventually, the entire loaf acquires structure. Now, suppose you know the temperature of the oven, the chemistry of the yeast, and the time the loaf has been baking. From that information, you can predict roughly how developed it should be. If you open the oven 10 minutes early and find a fully risen loaf, something in your assumptions requires attention. Perhaps the yeast is more active, perhaps the oven is hotter, perhaps the timer is wrong, or perhaps some process you ignored is accelerating the transformation. Cosmologists face the same logic. The cosmic microwave background gives us an exquisitely detailed measurement of the early universe. It tells us about the tiny density variations from which later structures emerged. We then evolved those initial conditions forward using gravity, dark matter, ordinary matter, dark energy, and the laws of physics. Computer simulations allow us to ask how many galaxies should exist at a particular epoch, how massive they should be, how quickly clusters should assemble, and what distribution of structures the universe should contain. The astonishing thing is that this works not perfectly, but remarkably well, which means that when a structure appears unusually early, astronomers cannot casually adjust every parameter until the problem disappears. The model is constrained by everything else we have measured. And this is what makes modern cosmology both powerful and unforgiving. You cannot change one gear without affecting the entire watch. Hold on to that image. The universe is not one equation tested by one observation. It is a machine whose parts must agree. Change the amount of matter and you alter structure, formation. Change the nature of dark matter and you alter how halos grow. Change the expansion history and you alter the time available for gravity to act. Change the properties of dark energy and late cosmic evolution shifts. Change the initial fluctuations and the cosmic microwave background notices. Every proposed solution sends consequences outward, and that brings us directly to the paradox. What does an early mature cluster actually mean? The first possibility is the least revolutionary. Perhaps we have underestimated how efficiently clusters can assemble. Astrophysics is complicated. Baryonic matter, the ordinary matter made from particles such as protons and neutrons, does not simply fall into gravitational wells like sand into a bowl. Gas cools, stars form, black holes grow, supernovae explode. Active galactic nuclei release enormous amounts of energy. Magnetic fields or plasma, radiation pushes matter. Feedback can either suppress or accelerate different processes. Our simulations are sophisticated, but they are still simulations. If some combination of gas physics and galaxy evolution allows cluster environments to mature faster than expected, then the fundamental cosmological framework might survive largely intact. That would still be important, but it would not rewrite physics. The second possibility is more interesting. Perhaps the dark matter scaffolding itself forms earlier or more efficiently than our simplified expectations suggest. Dark matter is one of the strangest ingredients in modern science. We infer its presence from gravitational effects. Galaxies rotate as if they contain far more mass than we can see. Galaxy clusters bend light through gravitational lensing more strongly than luminous matter alone can explain. The pattern of the cosmic microwave background also strongly supports the existence of a non baryonic matter component. And yet, we still do not know what dark matter is. No confirmed particle has been identified. That leaves enormous theoretical territory. Cold dark matter works extremely well on cosmic scales, but researchers have explored alternatives and extensions for decades. Warm dark matter, self interacting dark matter, ultralight particles, axion like candidates, primordial black holes, more exotic possibilities. An unexpectedly early massive cluster does not automatically favor any of these, but every measurement of early structure becomes another filter. A model of dark matter must not only explain galaxies today, it must reproduce the chronology of structure, and that chronology is becoming observable. Webb changed that. Before Webb, our view of the first several hundred million years was limited. Now we can directly study galaxies during cosmic dawn with a clarity that would have seemed extraordinary a generation ago. And the early universe is proving productive, perhaps too productive. Some of Webb's earliest reports generated headlines about galaxies that seemed far too massive, far too bright, or far too evolved for their age. Subsequent work showed why caution was necessary. Distances can change after spectroscopy. Mass estimates can change when emission lines, dust, star formation histories, and active black holes are modeled more carefully. Some apparently impossible galaxies became less impossible. This is how science is supposed to work. An observation produces tension, better data refine the observation, better models refine the interpretation. Some tension disappears, some remains. The cluster problem deserves exactly the same discipline. NASA itself did not announce the death of cosmology. It said the discovery would lead astronomers to rethink when and how the largest structures in the universe form. That wording is careful and powerful because the phrase when and how is where cosmology lives. Imagine a crime scene, the final state, where the objects are. You can measure temperatures, distances, velocities, and chemical fingerprints. But you did not watch the event happen, and your job is to reconstruct the sequence. Cosmology is forensic physics on the largest possible scale. The present universe is the scene, light is the evidence, redshift is the timestamp, and every telescope is a different instrument for reconstructing the history. When Webb observes a galaxy billions of light years away, it is not seeing where that galaxy is today. It is seeing the galaxy as it was when the light began its journey. Distance becomes time. The deeper we look, the earlier we see. That is why an ancient cluster is so valuable. It is not a fossil dug from the ground. It is a fossil we observe directly in the act of being young. Now, I want you to imagine a vast spider web stretching through darkness. At the intersections are luminous knots, and between them run nearly invisible filaments. This is the cosmic web. Galaxies are not sprinkled randomly through space. They trace an enormous network shaped primarily by dark matter. Dense nodes host clusters. Long filaments connect them. Large empty regions form cosmic voids. The architecture arose from tiny primordial density differences amplified by gravity over cosmic time. A surprisingly mature early cluster tells us that at least one dense node of this web became organized very quickly. The question is whether it is rare. This is crucial. Finding one unusual object is not the same as proving a population level crisis. In an enormous universe, rare events happen. And if you survey a large enough volume, you will eventually find something in the tail of the probability distribution. Cosmologists therefore ask not merely, is this object surprising? And they ask, how surprising? One in 10, one in 1,000, one in a billion. Is the survey volume large enough that finding one is expected? How certain is the estimated mass? How secure is the redshift? How mature is the hot gas? Could selection effects have made this kind of object easier to detect? These questions can sound less dramatic than saying physics is broken, but they are the questions that decide whether physics is actually in trouble. Here is the hard truth. An anomaly becomes revolutionary only when it survives accounting. Every source of uncertainty must be counted. Every alternative explanation must be tested. Independent observations must agree. Similar objects should begin to appear, and the statistical significance must grow. This is why I find this period in astronomy so fascinating. We are not watching a textbook collapse, we are watching a stress test. The standard cosmological model is being pushed into an observational regime that was previously inaccessible, and Webb keeps pushing. And the deeper it looks, the closer we get to the first galaxies. The closer we get to the first galaxies, the less time nature had to build them. And eventually, chronology itself becomes the experiment. At some point, if we repeatedly find structures that are too massive, too mature, and too numerous to arise under the expected growth history, the pressure will move away from astrophysics and toward cosmology. Uh, and then the questions become more fundamental. Were the initial density fluctuations different from what we assumed? Does dark matter behave differently at early times? Did dark energy have a role earlier than expected? Is gravity exactly described by general relativity on every cosmological scale and epoch? Could there be additional fields influencing structure growth? Now we are approaching the territory implied by the phrase rewrite physics. But notice the progression. One does not jump from an image to a revolution. One climbs observation, measurement, population, tension, failed conventional explanation, new theory, prediction, test. That ladder protects science from our appetite for drama, and it also makes genuine revolutions far more powerful when they arrive. Consider gravity. Einstein's general theory of relativity has survived more than a century of extraordinary tests. Light bends around mass. Clocks run differently in gravitational fields. Mercury's orbit is explained. Black holes behave remarkably close to relativistic predictions. Gravitational waves travel across the universe and reach our detectors with properties consistent with the theory. But cosmology asks general relativity to do something audacious. We extrapolate it across the entire observable universe, across billions of years, across enormous scales, and then we add dark matter and dark energy to match what we see. The result works extraordinarily well. Yet, dark matter and dark energy dominate the cosmic energy budget, and we still do not know their fundamental microscopic nature. That should keep us humble. Our equations can successfully describe a universe whose primary ingredients remain unidentified. So think about that. We know how the invisible architecture behaves better than we know what it is. The iron filings reveal the magnet, but we still have not opened the table. An early cluster probes at hidden machinery. If structure growth differs from expectation, one possibility is that gravity itself behaves differently under some conditions. Modified gravity theories have been proposed for many reasons, including attempts to explain galaxy dynamics or cosmic acceleration without some conventional dark components. Most face severe observational constraints. Any replacement for general relativity must reproduce all of relativity's successes while improving the places where tension remains. That is an almost impossibly high bar. Still, early structure is one arena where deviations could potentially reveal themselves. If gravity were effectively stronger during certain cosmic epochs, matter could gather faster. If an additional field influenced clustering, halo formation could change. If dark energy evolved differently, the expansion history and structure growth could shift. These possibilities are speculative, but they are testable in principle, and that is the dividing line that matters. A scientific possibility must leave footprints. The cluster abundance as a function of redshift, the distribution of masses, the temperature of intercluster gas, the strength of gravitational lensing, the clustering pattern of galaxies, the cosmic microwave background, weak lensing across enormous surveys. Each measurement becomes another constraint. No single observation gets to rewrite the rules alone. The entire universe votes. And now I want you to look at your hand. It appears solid, but nearly all of its volume is structured by quantum fields and electromagnetic interactions. The atoms in it contain nuclei forged in stars. Those stars formed inside galaxies, and those galaxies grew within dark matter halos. Those halos emerged from primordial fluctuations, and those fluctuations were already present in the infant universe. Your hand is connected by an unbroken physical history to the earliest structures we are discussing. This is not poetry, it is genealogy, cosmic genealogy. If our model of structure formation changes, the story of how matter became complex enough to produce us changes with it. That is why these distant objects matter. They are not merely remote curiosities. They are earlier chapters of the same process that eventually produced the room around you. Let us return to the cathedral. At the beginning, a tiny light appeared high above us, and then we realized it was a city of galaxies. Now imagine the walls around that city becoming transparent. You can see invisible dark matter extending outward. You can see gas falling inward. You can see shock fronts heating plasma. You can see galaxies orbiting inside a gravitational well. You can see filaments feeding the structure from the surrounding cosmic web. And then you look at the clock on the cathedral wall, and the clock says the universe is only about 1 billion years old. That is the disturbing part. Not that the city exists, that the city had enough time to become a city. NASA's results suggest that the process of assembling some of the universe's largest structures was underway substantially earlier than many astronomers had expected. It is a timing problem, and timing problems can become physics problems. Suppose future Webb and Chandra observations find many more such systems. Suppose their masses are confirmed. Suppose hot intracluster gas is repeatedly found at epochs where simulations predict mostly immature protoclusters. Suppose gravitational lensing independently confirms deep potential wells. Suppose the abundance becomes difficult to reconcile with the expected growth of structure under standard parameters. Then cosmology faces choices. Maybe the initial conditions need adjustment. Maybe the matter content needs adjustment. Maybe the dark sector is more complex. Maybe early feedback. Physics has been misunderstood. Maybe gravity itself needs an extension. Or perhaps improved simulations reveal that the apparently impossible structures were possible all along. That last outcome would not be a disappointment. It would mean the observation taught us something real about nonlinear structure formation. Science advances whether the anomaly survives or dissolves. What matters is that nature decides. There's another reason these observations arrive at an important moment. NASA's Nancy Grace Roman Space Telescope is designed to survey enormous regions of the sky with high resolution over a very wide field. Webb is extraordinary at deep, detailed observations. Roman will be extraordinary at statistical scale. That combination matters because the difference between an odd object and a cosmological crisis is population statistics. Webb can find a needle. Roman can tell us how many needles exist. If rare massive structures in the early universe are much more common than Lambda-CDM predicts, wide area surveys will expose the discrepancy. If they are genuinely rare, the apparent crisis may shrink. This is how the next generation of surveys could transform the question. We are moving from isolated surprises to census taking, and censuses are dangerous for theories. A theory can explain one strange object with an unusual history. It cannot easily explain thousands of them if they systematically violate its predictions. Hold on to the loaf of bread. One loaf rising too quickly may be an accident. An entire bakery rising too quickly means your recipe is wrong. This is where human intuition entirely breaks down because cosmic structure formation is not a simple stopwatch. Gravity competes with expansion. Dark matter collapses hierarchically. Gas dissipates energy. Feedback redistributes matter. Mergers accelerate growth. Environment matters. Statistics matter. And the result depends on an enormous coupled system. Our brains want a single cause. The universe often gives us networks. That is why numerical simulations are indispensable. Researchers create synthetic universes inside computers. They begin with initial conditions consistent with the early cosmos. They evolve billions of particles or fluid elements under gravity and hydrodynamics. They generate dark matter halos. They populate galaxies. They heat gas. They compare the synthetic sky with the real one. Every new observation becomes a test. If simulations consistently fail to produce what telescopes see, theorists investigate why. Sometimes the answer is mundane: resolution, calibration, missing feedback, incorrect assumptions about star formation. Sometimes the discrepancy points deeper. The history of physics is full of both outcomes. Mercury's anomalous orbit became a doorway to general relativity. The ultraviolet catastrophe helped force quantum theory into existence, but other anomalies vanished when instruments or models improved. We do not know which category today's early structures will join. That uncertainty is not weakness, it is the actual frontier. The phrase could rewrite physics should therefore be understood precisely. Could, not did. The observation has opened a logical path toward deeper revision if the tension strengthens. The next step is not celebration, it is pressure, more data, more clusters, more spectroscopy, better mass estimates, better X-ray measurements, better lensing maps, larger simulation volumes, more careful statistical comparisons, and then we discover whether the door is real. Now I want you to imagine one final object, an old map. The coastline is beautifully drawn. The major rivers are accurate. Cities are placed where they belong. For generations, travelers use it successfully. Then explorers reach the edge and discover an island that is not on the paper. The existence of that island does not make the entire map useless. It tells you where the map ends. This is how I think about modern cosmology. Lambda-CDM is not a crude failure waiting to be discarded. It is one of the most successful quantitative frameworks humans have ever built for describing the universe. But successful maps can still have edges. Dark matter remains unidentified. Dark energy remains mysterious. The Hubble tension remains under intense investigation. The earliest galaxies continue to test models of rapid formation, and now unexpectedly mature early clusters are adding another line of inquiry. These may turn out to fit the map, or they may help redraw a corner of it. Either result is knowledge. Think about the sheer weight of this. The photons Webb captures left their sources billions of years before Earth existed. The X-rays Chandra detects were emitted by gas heated in gravitational structures from an ancient universe. Those photons cross expanding space. They survive galaxy formation, stellar evolution, planetary formation, biological evolution, human civilization, and the construction of machines sophisticated enough to catch them. And then a detector records them, and a number enters a computer. An astronomer compares the number with a model. And suddenly, an event that occurred near cosmic dawn can challenge an equation written by someone on Earth. There is something almost absurdly beautiful about that. The universe can argue with us across time, and it does. Newton gave us gravity as a force acting between masses. Einstein replaced that picture with curved spacetime. Quantum mechanics transformed matter into probabilities and fields. Modern cosmology revealed that ordinary matter is only a small fraction of the cosmic inventory. Each step began when observation refused to remain inside the old conceptual box. Now, perhaps we are entering another period of accumulation, not one decisive contradiction, many small pressures, early galaxies, and early black holes, early clusters, precision measurements of expansion, dark energy surveys, gravitational wave astronomy, new maps of matter. Each is asking a slightly different version of the same question: how complete is our picture? Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless dedication to separating surprise from proof. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel, there you help make these long-form explorations possible. But before we end, return with me to the images we have carried through this journey. And the cathedral taught us scale. The iron filings taught us that invisible matter can organize what we see. The skyscraper taught us why maturity requires time. The loaf of bread taught us that growth has a rate. The spider web showed us the cosmic structure that gravity builds. And the old map reminded us that a successful theory can still have an edge. NASA has not captured the death of modern physics. It has captured something more useful, a test, a massive structure from an unexpectedly early chapter of cosmic history, mature enough to make astronomers reconsider how quickly the largest structures in the universe can assemble. If future observations show that this object is merely rare, our map becomes sharper. If they show that objects like it are common, the pressure on the map grows. And if the pressure eventually forces us to change our understanding of dark matter, gravity, or cosmic evolution, then the revolution will not have begun with a declaration. It will have begun with a faint ancient glow, a light in a dark cathedral, a structure that arrived too early, and one quiet question: